Okay guys, this is Sumit here. Again, we are using the textbook 12th edition, Operations Management and Sustainability and Supply Chain Management by Heizer, Render and Munson. We are going to do the chapter 4, forecasting. Now this is the first chapter that is quant heavy and is a typical representative of operations management course. In the forecasting, the lecture notes are posted for you in the iLearn. We are going to go through the quantitative approaches or the quantitative methods, namely being naive, moving averages, exponential smoothing, trend, and linear regression. So let's start with some of the problems that are representative, so then we can start practicing. A few summaries. Trend happens over longer periods of time. Cyclical happens usually beyond multiple years. Seasonal is usually smaller periods of time within a year. Random is something that does not have a whole lot of pattern attached to it, especially in the short term. On the long term, even though the data might seem random, but it might represent some type of trend that is observable. Now, seasonal index helps us derive the smaller fluctuations that are associated with tradition or seasonality within a year. Okay. Now we are going through this. We're going to go through multiple formats in the example one by one. Before we progress there are three forms: mean absolute deviation, mean squared error, and mean absolute percentage error. These three measures help us determine as to which of the methodologies out of weighted moving average or exponential smoothing or linear forecasting, linear regression is better for the concerned data. Okay, and that's about it. The other few things associated with linear regression are the correlation coefficient, and the last thing would be the multiple regression analysis. Okay, now first thing, let's start with easy part. So this is one of the questions wherein we are given the month and the sales, and the first thing they've said is plot the sales data. Now the reason they're giving us these small questions is such that we tend to develop the small pattern or the baby steps such that it comes to our habit. Now the reason they're asking us to plot the data is such that it is observable to us, so then we can observe if there is any pattern in it. So let's say insert scatter chart. Now just to be sure, I'm going to select data and make sure, okay, January, February, these are on my horizontal axis. Okay, and let's say in add chart element, where's legend? Okay, so now I know sales is on my vertical axis, on the horizontal axis is are the months. Okay. Now once you've plotted the data, it is clearly visible that there's a usual dip around the fourth month, which is April. After that it goes slightly increasing from month 4 till month 12. Okay, so that's a good information to know, because we know the sales are not random, it's not increasing and decreasing erratically. So that is what we can observe from the first question that asks us to plot the data. Now the second question is about the quantitative, which takes the approach of using various methods. The first one being naive method. So if we were to plot the data using naive method for the January sales, it says, so the January sale would be this one here. So theoretically these are the 12 months given to us. So let me do the usual thing. We color the given data in gray, and this would be our calculated one in blue. So using naive methodology suggests it's equals to exactly the actual sales of the previous time period. So previous time period was the December of the last year. Okay, so the sales for the January using naive method would therefore be 23. Okay, so let me color this yellow. Now then comes using 3-month moving average. So 3-month moving average. So 3 months moving average means that we have to take average of the last 3 months, 1, 2, 3. Okay. Now one key thing to notice here is the maximum we can go back, if we were to, is April. But since it is not asked of us, otherwise we can go up until this point, but not till this point. Why? Because this, if you see, goes on to 21, 20 in sales there. So this is erratic calculation because there's no point in taking average of an alphabetical value. However, since this is just for demonstration, we will stop here. This is what concerns us. So based on moving average, monthly the January sales for the next year is 21.3. So let me make this like that. This is equal to this. Now when we took the 3-month moving average, the inherent assumption was that both all December, November and October, they all had equal weights to them, which would be in this case 1/3 of 100%, so 33% each. However, in the next part we are given the 6-month weighted average. This is similar to what we did in chapter 2, wherein we had a factor rated methodology. So let's see, first we are given the weights. Weights are given to us such that 6 months, so 0.1, 0.1, 0.1, 0.2, 0.2, 0.3, and it is also given with the heaviest weights applied to the most recent month. So it's appropriate in writing it like this because 0.3 is associated with the recent most, which would be December. So in this case, therefore, our sales becomes sum product of the weight times the sales. Okay, so what it does is, it means we are doing the sum of the products between 17 times 0.1 plus 18 times 0.1 plus 20 times 0.1 plus 20 times 0.2 plus 21 times 0.2 plus 23 times 0.3. So instead of doing all those calculations individually, we are doing them all together in single cell. Okay, so this is 6-month weighted average. Okay, so you're done with this. So this is equals to this value here. Now the exponential smoothing using an alpha of 0.3. Let's see, it'll be good to show you guys how to insert alpha. Oops, let me insert it here first. Insert symbol, and let's see if I can find alpha here. Okay, insert. So make sure, remember Greek and Coptic and normal text, that's where you get to see alpha. If it's not here, if you keep this heading and this subheading, you should be able to find it somewhere close by here. Okay, so insert alpha, close. Then I can bring it back here. Alpha equals to 0.3. Now remember, alpha will always be between 0 and 1. Alpha can be taken as the percentage of correction you want to make to the previous forecast. So if we were to look for the formula, exponential smoothing, okay, there. So exponential smoothing allows us to forecast for any time period which is equals to the forecast of the previous time period plus a certain percentage correction to the error, where an error is defined as the actual minus forecasted. So if you look at it from the perspective of the previous period, this is how far off we were in the last period. So this was our error. So if the data is highly fluctuating, which means we may have been very far off in terms of predicting. So if that is the case, then we make higher correction, which means there would be a bigger value of alpha, which means it would be more towards the 1. So it could be 0.8, 0.85 or 0.9. If this error happens to be small and we were somewhat satisfied from the previous period's forecast, then we'll make small adjustments, so it will be more close to the 0. And once you do that, you get a correction term, you add that to the previous forecast, and that is how you get the forecast of this year. Okay, so let's come back here and do the exponential. Now let's say I had alpha somewhere here. Okay, I'm going to put this here, but I'm going to bring this number here so then I can make use of it in calculations. So first thing, I need, in order to use this, I need the forecasted value for the previous period, because you remember it makes a correction to the previous forecast. So let's read it again carefully. Exponential smoothing of alpha equals to 0.3 and September forecast of 18. So they have given us a starting point such that the forecasted value for September can be used as 18. Okay, so which means starting October we can make the new forecast using exponential smoothing, which is equals to the previous forecast plus alpha. I'm going to freeze it, hit F4, times parenthesis. Now this is actual minus actual minus forecast of the previous period. So actual minus forecast of the previous period. So that completes our formula. Now we can bring this down like this, and that's our answer for the January. Now remember, we still cannot go any further than this, because in this case it is using wrong references. So the maximum we can go is the January of this year or next year. The next one is trend projection. So in order to do the trend projection, here, so now we are going to do trend projection. Okay, now in order to do the trend projection, let me bring all of this data here, Control C after selecting it. Then I'm going to paste it using values such that I convert this into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 13th. And so this becomes our sales becomes our dependent variable. It's called dependent variable, and months would be our independent variable. Okay, or in other words, this would be y and this would be the form of x. Now this comes from the format of y equals to ax plus b. Now if you remember from the chapter, b is your constant, a is your coefficient, x is the variable, and x is the independent variable. So the way we will use this equation is, what is the sale in 13th month when x is equals to 13? So we are going to find that out. Okay, so for now I'm going to delete this because it helps me with the keyboard selecting all the data together. So control down arrow, I know this is where it will stop. Now there are a few ways to do this. If we were to select the data, first way is to again either use the scatter plot. Let's use the scatter plot. Select, right click, add a trend line. Okay, now the moment you add the trend line, you have the option to say display the equation on the chart and display the R square. That is how you'll get to see this. Now using this, you can identify using this equation that so if you compare this with this, you can find out that your slope is 0.3986 and your constant is 15.5. Okay, so let's write them down somewhere. The slope is equals to 0.3986, and constant is, it's the constant, I mean you can also call it intercept, is 15.576. okay, so using this, if you wanted to, you can find out here in the 13th month your sales would be slope times x, which is 13th, plus constant, okay, which is 20.7578. so using this, you can say that your January sales would be equals to 20.7578. Now theoretically, I'm gonna drag and drop it here. If this is how we calculate it, it's dependent on the slope, the constant, and the time period. Now remember, we could not have done this if we were to use month values in alphabetical form, because this is the 13th period, not the same January. This January is not same as the original January of the last year. Okay, so having said that, if we wanted to go further, then first thing is, I'm going to do this again. This I'm going to hit F4 times the time period. I'll leave it as is without unfrozen, plus the constant, and I'm going to hit F4 and freeze it. So if I was to stretch it down for the 14th month, the 15th month, the 16th month, and the 17th month, so theoretically I am able to predict or the forecast for the months moving forward way far ahead than the present time. However, the farther you go, the less accurate it is, especially when your R square is 0.2072, which is considerably relatively a low value, which means the the change in y is only explained to the extent of 20% by change in x's. Okay, so it's not a very robust model. It means that there are some other things that our sales is dependent on. In other words, the changes in sale is only explained 20% when we move from one month to another. Rest of the change in sale is explained by the variables that we have not accounted for yet. Okay, now we calculated the slope and constant using the graph value. Now what if your data is too big wherein you can't select all of it, or it's not something reliable, or not all the data is together? Then in those cases you can also calculate equals to slope. You can use that as a formula. Known y's, so known y's would be, remember, only up until 12th month, comma, known x's. Known x's would be your independent variable. Make sure you select the same range for both x and y. So that gives you the slope again, which is same here. Also you can calculate intercept for the known y's along with the known x's, and you get the same intercept again. Okay, value for the intercept. Now you can use these values to calculate the sales here the way we did, using slope and constant here, or let me call it intercept as your textbook uses. Okay, so let's see, coming back to our question, we use the trend projection, which with the data given, which method would allow you to forecast next March sale? So the only way we can come back here is Jan, February, March. Oops. So this is the only method that allows us to go till March. So the way you would answer that question is that using trend projection is the only method that allows us to forecast the sales for the month of March. No other methodology allows us to go that far. So that's about this question. Okay, so the next one is wherein we will be using those three measurements of mean absolute deviation, mean squared error, and mean absolute percentage error. Okay, so let's move these somewhere. Okay, here, and given information is 93, 94, 93, 95, 96, 88, and 90. This is yesterday. Okay, till this point this is yesterday. Forecast the high temperature today using 3-day moving average. Okay, so it's a moving average using 3-year period. So if that was yesterday, then this would be today. Again, the given temperatures, you can color them in gray. So for today, I can easily calculate average of the last 3 periods. Simple, done. Now, when we calculate forecast the high temperature today using 3-day moving average, forecast the high temperature using 2-day moving average. If that's the case, since it's a simple average, we take the average of the last 2 numbers here. Calculate the mean absolute deviation based on 2-day moving average. So now that this has been asked of us, we will have to make some space here. So this is equals to this. This one is equals to this, and this being the answers. So I'm going to highlight them. Now, in order to calculate mean absolute deviation, we need to first calculate the error between the actual values and the forecasted values. Once we have the actual and forecasted value, the difference between the two would be the error, which is also called as deviation, and the absolute value of the deviation would be absolute deviation. Then you take the mean of those absolute deviations, that becomes your mean absolute deviations. So let's see how this is. Okay, so first let me make some space here. Now this is for 3-year moving average. So let's see how far can we go. That's it. That is how far we can go. So this one goes for 3. We can't go any further. And this, I'm going to uncolor it. This one, I'm going to move it somewhere here. So if this is the forecasted value for moving average with a 3 month period or 3 days period, then our absolute deviation would become, let me get it here closer, would be, let's do first deviation. Okay, equals to actual minus forecasted. This is how far off we were, and then we calculate absolute deviation, which is equals to absolute values of the deviation. Now you could have done that in single cell, but I'm just trying to show it to you as to how it is done. And then we have to calculate the average or the mean of these absolute deviation. So this becomes MAD for 3-month moving average. Okay, now this absolute deviation is also called as error. Okay, and we can use it again. Now the next thing we have to do is mean squared error. Now since this is the error, therefore you can use it again to say this raised to the power 2, and if you were to copy this down up until this point and do the same thing again, equals to average of these numbers, that gives you mean of the squared errors. Okay, so that is, and this I didn't write it all, squared errors. Now just to give you a feeling, let me see in the PowerPoint. So see, this is how it is represented in the formula, right? So mean absolute deviation is summation of these vertical lines represent the absolute values, which means we ignore the positive or the negative sign. Actual minus forecasted divided by n. Okay, so this is what we have done here. Actual minus forecasted is done here. So 95 minus 93.3. Then we take the absolute values. That gives us the top part, actual minus forecasted absolute values. Now summation of all such values divided by the number of values we are summing up is nothing but average. So that is what this is. So mean absolute deviation here is one calculated value, and then the mean of squared errors is what we have done here. So the forecast errors squared and sum them up divided by the number of values we are summing up. So that's what we have squared the errors. So the square of errors is coming from this. This was error. Even if this was negative or positive, even though it is not mentioned here, right? But any negative number squared will become positive anyways, right? So this is sufficient for us. Now the next thing for us is the mean absolute percentage error, which means that again this is the absolute error or deviation divided by the actual. So this absolute vertical lines, absolute values, will take care of any negative sign, so it will always be positive. Actual minus forecast divided by the actual value, and we have to represent that in percentage terms, and then we take the average of those percentages. That is how it is called mean of absolute percentage error. So first we calculate the percentage error in absolute form, and then we take the mean of it. So let's say this is percentage error. Now we did calculate error here, right, divided by the actual value. Okay, since this is already done, now we can multiply the numerator part here, okay, by 100. Now this is in percentage terms. So we were 1.75% off on this day when the temperature was 95, and yesterday we were 3.3% off in predicting. At this point, if you were to calculate average deviation in terms of percentage, that gives us mean absolute percentage error, which is this. So now all of this is based off forecasted value for 3-day moving average. Now we will do the same thing for moving average for 2 periods. In this case, no fail, and I can go up until this point, because if I was to go any further than this, then I would be referring to one empty cell here. So that is the max I can go. So if it's a two-day moving period, I can only start from 3rd day onwards. Okay. Now if this is the case, then I can repeat the same process by calculating the deviation, which would be in this case actual minus forecasted up until this point, and then I can calculate absolute values of these. That gets me here. If I was to square these, I will have what you call squared errors raised to power 2. And if I was to make a percentage of the error, let me multiply this time 100 divided by the actual values. That gives me the percentage error. Now if I was to take average of all these numbers, average of all of these, the first one gives me mean absolute deviations, the next one gives me mean squared errors and mean absolute percentage error. So now we have the 3 indices that tell us which forecasting method is better. So if we were to compare our values, let me bring them all to the same format. or maybe we shouldn't lose the decimals so much, so let's keep them here because the numbers are already too small. So comparing mean absolute deviation, if we were to forecast using 3-day moving average, we were on an average off by 3.3, either up or high, up or low. So either we overestimated or underestimated on an average by 3.3. If we were to use the 2-day moving average, then we on an average we either overestimated or underestimated by 2.7. Since MAD for 2-day moving average is less than the MAD for 3-day moving average, this seems to be better. Now let's see if this is true for all the other ones. Mean squared errors. This, what it does is it amplifies the error, because whatever error we had, we squared it, so it become larger. Therefore, the average of the large squared errors will also be large. So the same 2.7 here is now reflected in amplified manner, 13.35 versus 15.05 for the 3-day moving average. Therefore, again, 2-day moving average is better. Now, if we were to talk in terms of the percentage, now percentage wise, let me see, did I do this right? Yes. So in terms of percentage wise, we can see it's 3.68 for the 3-day moving average, wherein this one is coming out to be a little too big. Yes, but it is correct. Is it? Error. Okay, that's where this is not correct. Error is this one in the column. Chose the wrong column, sorry, my bad. So again, where were we? Mean squared error, this 2-day is better. Mean absolute percentage error, again 2-day moving average is better forecast methodology than the 3-day moving average. So this is where MAD, MSE and MAPE come in handy. Okay, so next we are going to practice the seasonality, wherein first we need to calculate the seasonal index. Now in this case, I think this is 4.26 in the end of the chapter problem. In this case, we are given the seasonal sailboats that were sold by the manufacturer. Now it is given to us, but there are 4 quarters in a year, and we are given like 4 quarters and for next 4 years. Now they've asked us how George has forecasted annual demand for sailboats in year 5 will be equals to 5,600 sailboats. Based on this data, what would be the demand for the sailboats in the spring of that year? So calculating annual demand for the next year, however they did that, moving average or exponential smoothing. Now in this case, since it is given to us, it's none of our business, but what is critical for us is to find out what would be the sales in the spring of the 5th year. So first thing is we divide this in few steps. So the step 1 I would suggest is to calculate the average quarterly. Okay, so let's say average quarterly sales. Okay, and I would call this step 1. So first thing is, let's find out what the average quarterly sales is. Now this would be by the seasons, so there we have it. Now also we know the demand for the particular year would be, for the year 1 it was this much. Yeah. Therefore the average annual demand is 5,000, correct? If this is the average demand for the uh, whole year, then what would be, as a step 2, what would be the average quarterly demand, given that the average annual demand is 5,000? So there are 4 quarters in a year, so it'll be and I'm going to freeze it because it'll be the same, 5,000 by 4. So this would be the expected average quarterly demand given the annual demand of 5,000. Now this is it. Once you have this, then the step 3 is to calculate the actual average for the quarter divided by the uniform average for the quarter, which is coming from the average demand. Yeah, that gives us the seasonal index, which means this is almost close to the uniform demand. This is slightly above the average quarterly demand. This is a lot more than the average quarterly demand, and fall is the dull season wherein only 50% of the average sales happens. So now that we have the 5600 as the given demand for the year 5, so this is for the year 5, therefore whatever the annual sales is, that times the seasonal index. Therefore this 5,000 would be distributed according to the seasonal index, such that the sum total would still be 5,000, but it's distributed just the way the historic sales in various quarters have been in the past. So this is how we take care of the seasonality. Okay, that's all about it. If you have any problems, I'll be online on Tuesdays 4 p.m. Have fun. Bye.